Today we will discuss positive displacement pump. Positive displacement pump. Actually, we have discussed about pumps in general, and there are two categories of pumps. One is rotodynamic and the other one is positive displacement. The rotodynamic pump, we have discussed one classical example of centrifugal pump, and the working has been discussed in the earlier sessions. And now we will deal with positive displacement pump. For a positive displacement pump, actually there will be an enclosed area, and secondly there will be a moving part of the pump, actually coming in contact with the fluid to be displaced. So in the case of a rotodynamic pump, there will be a rotor actually rotating in the fluid, and in the case of positive displacement pump, there will be an enclosed area. For example, there will be the enclosed area is actually a cylinder, and the moving part is actually a piston. I will show you the figure. This is the figure of a centrifugal pump. Reciprocating pump. So you can see the cylinder here. This is the cylinder, the enclosed part which we are discussing, and this is the piston, which is the moving part. The piston has got a connecting rod attached to a crank, which is the rotating element. Actually, for the pump, it will be the motor. The rotating prime mover will be the motor. It will be attached to the crank, and the crank will be rotating. And as the crank rotates, the piston reciprocates inside this enclosed cylinder. The working is similar to the syringe, which we are familiar with. When the syringe piston is moved, a vacuum is created in the other side of the piston, and the fluid can be sucked in. That is the working principle of a reciprocating pump. This is the enclosed cylinder, this is the reciprocating piston, this is the connecting rod, and this is the rotating crank. As the crank rotates in the from 0 to 360 degrees in the clockwise direction, the piston will be reciprocating from the inner dead center to the outer dead center. The leftmost position of the piston is known as IDC, the inner dead center, and the outer dead center, the piston will be moving along these two positions. So from inner dead center to outer dead center, the length is known as the stroke length. And the suction pipe is attached here. This is the suction pipe which will be attached to the sump, and the height from the center of the cylinder to the free liquid surface is known as suction lift. And this is the delivery pipe, and the center of the cylinder to the free level of the tank will be delivery lift. Suction pipe is having a suction valve, and delivery pipe is having a delivery valve. The most important thing to be remembered is that there will be only suction for this is known as a single acting reciprocating pump. That means in one stroke there will be only suction, and the next stroke it will be the delivery. So the delivery will be intermittent. So these type of pumps are usually used for high heads and with low delivery. Now if you look on to the different types of reciprocating or positive displacement pump, we can see the different types of positive displacement pumps here. The main classification is a reciprocating type and the second one is rotary type. In the reciprocating type, there are reciprocating pumps and diaphragm pumps, and for a rotary type you can see 4 types: gear pump, vane pump, low pump and screw pump, of which we are concentrating on a reciprocating pump. And for that reciprocating pump, the main components are here. Now we will look on to the working of the reciprocating pump. As the crank rotates from 0 to 180, the piston will be moving from inner dead center to outer dead center, that is the stroke length. Then on the left side of the piston, a vacuum will be created and the suction valve will be opened and water will be sucked in to the left side of the piston. Now the piston is in the outer dead center. The crank now rotates from 180 to 360. The piston moves from outer dead center to inner dead center, pushing the fluid, making the delivery valve open and making the delivery to the required height. That is the actual working of the reciprocating pump. As we have already said, the one thing to be remembered is that in a single acting reciprocating pump, the delivery, the flow will be intermittent. And another important thing to be remembered is that here no priming is required. Actually, the moving part of the pump is in direct contact with the fluid to be displaced. No priming is required, and the speed of the pump is the main primary element which decides the delivery or the flow, and it is independent of the delivery pressure. Another important thing to be remembered is that the delivery valve should not be closed in this type of pumps. In the case of centrifugal pump, it should be started at no load, keeping the delivery valve closed. But in the case of a reciprocating pump, as it is directly pushed, if the delivery valve is closed, it will cause damage to the pump. So no priming is required and delivery valve should not be closed. So that is the working of a single acting reciprocating pump. Now we look on to a double acting reciprocating pump. You can see the figure here. This is a double acting reciprocating pump, in which you can see this is the piston and this is the cylinder with two delivery pipes and two delivery pipes and 2 suction pipes. So when the piston moves towards the right, the suction will happen in this suction pipe, and simultaneously on the other side of the piston, delivery will happen through D2. So when the piston moves from outer dead center to inner dead center, again the suction will happen on the right side and delivery will happen on the left side simultaneously. So that means twice the discharge is possible than a single acting reciprocating pump. So the flow will be continuous in this particular case. So that is the general working of a reciprocating pump. Now another important point on this topic is actually slip. You can see what is a slip. Slip means actually before going into slip, we will discuss what is the discharge, what is the actual discharge formula for discharge in a reciprocating pump. So volume of water pumped will be equal to area of the cylinder into length of the stroke. This is the volume of water pumped per rotation. When the crank rotates once, when the piston moves from inner dead center to outer dead center and from outer dead center back to inner dead center, one rotation of the crank is complete, and the volume of water pumped per rotation is area of the cylinder into length of the stroke. So if N is the rotations per minute, then n by 60 will be the rotation per second. So volume of water pumped per second will be equal to ALN by 60. This much meter cube per second. So this is the theoretical discharge QTH for a reciprocating pump, that is ALN by 60 meter cube per second. This is the theoretical discharge. And now the weight of the water pumped, weight of water pumped will be equal to, we know that mass is rho q, so rho qg will be the weight of water pumped. So what will be work done by the pump? Work done by the pump will be equal to weight of water pumped into total lift. Total lift, that is equal to rho qg into hs plus hd, the suction lift plus delivery lift. So rho qg into hs plus hd will be the theoretical power or work done per second. This is the power done by the pump or work done per second by the pump is equal to rho qg into hs plus hd. And this q here is ALN by 60 meter cube per second. That is the theoretical discharge. That is the theoretical discharge. Q here is ALN by 60. That is the theoretical discharge. So QTH is equal to rho GQ QTH is equal to ALN by 60 meter cube per second, and power done by the pump is equal to rho GQ into HS plus HD. So these things need to be remembered. Another thing is that another important point is known as slip. Slip is equal to Q theoretical minus Q actual. This is the Q theoretical which we have discussed, ALN by 60 meter cube per second. But the actual discharge will be less than the theoretical discharge because of other constraints. So slip is actually the difference between QTH minus Q actual. So what is another thing is percentage slip. Percentage slip will be QTH minus Q actual by QTH. This QTH this slip can be negative. This percentage slip in the case of a reciprocating pump can be negative. Negative. That means slip will be negative when Q actual is greater than QTH. When will be Q actual greater than QTH? Percentage slip means QTH minus Q actual by QTH. That can be negative in the case of a reciprocating pump. That will happen when Q actual is greater than QTH. And when will this happen? When will Q actual be greater than Q theoretical? That will happen on these three cases. When the suction pipe is too long, when the delivery pipe is short, and when the pump is running at high speed. That means in the case of a reciprocating pump, when the suction pipe is too long, when the delivery pipe is short, and when the speed of the pump is very high, what happens is that the momentum of water flowing from the suction pipe will take the water directly into the delivery pipe without entering into the cylinder. So the momentum of the suction pipe being very long, the momentum and the speed of the pump being very high, the momentum of water from the suction pipe just pushes the delivery valve open and directly enters into the delivery pipe. So the theoretically assumed discharge is not actually accounting these type of phenomena. So the actual discharge in this particular case will be more than the theoretical discharge. In such cases, the slip will be negative. The slip will be negative. So when the suction pipe is too long, when the delivery pipe is very short, and when the pump is running at high speed, the momentum of the liquid in the suction pipe is large enough to open the delivery valve before beginning the delivery stroke. So in this case, the actual discharge will be more than the theoretical discharge. Okay. Now we are moving on to another important topic known as the indicator diagrams. So this is an indicator diagram for a simple indicator diagram. This is known as simple indicator diagram for the reciprocating pump. You can keep in mind that this is the simple indicator diagram. This is not the actual indicator diagram. This is the simple indicator diagram. Indicator diagram means the pressure head developed inside the cylinder of the reciprocating pump along the stroke length is actually plotted to a graph. So the pressure head in the cylinder will be on the y-axis and the stroke length will be on the x-axis. So that plot is known as simple indicator diagram. So you can see here, this is the atmospheric pressure head, 10.3 meters of water. So y-axis is pressure head and the pressure head inside the cylinder, and the stroke length of the piston is shown in the x-axis. So this middle line shown here is the atmospheric reference line, atmospheric pressure head. So of course, when the stroke length, this is the theta is equal to 0 position, that means the piston is at the inner dead center, and this is the crank is at 180, half the rotation of the crank. So the piston will be completing one stroke along L and reaches outer dead center. So this is the suction. It will be below atmospheric pressure, and it is assumed that along the stroke length the vacuum created is uniform. So from 0 to 180 position of the crank along the stroke length there is a vacuum created below the atmospheric pressure. It is equal to suction head, which will be a negative head, and that will be uniform line. And you can see this is the delivery stroke from outer dead center to inner dead center. So the piston is actually at 180 position, you can take it 0, and this is the 360 degree, we can take it as 180. So from the piston moves during the delivery stroke, again it is considered that high pressure is created, and that pressure pushes the water to the delivery, and it will be above the atmospheric pressure, and it is considered to be uniform along the stroke length. So this is simple indicator diagram, but the actual indicator diagram will not be like this. There will be other pressure heads also involved, and there are two other pressure heads involved. The first one being the acceleration head, and the second one is frictional head. So first we will look on to what is acceleration head. In explaining that, we have to understand that the piston moving along the stroke length is not uniform. The movement of the piston in the cylinder is not uniform. When the piston moves from inner dead center to outer dead center, it is actually following a simple harmonic motion. That means during the first half of the stroke, from say here inner dead center to the middle of the piston, middle of the cylinder at 90 degrees, the piston is actually accelerating. Then from 90 degrees to 180 degrees, that is from half of the cylinder to the outer dead center, the piston will be retarding. So here from this position to the center of the cylinder, the piston will accelerate, and from here to here it will decelerate or retard. This is because as the crank is rotating, this reciprocating motion of the piston can follow only a simple harmonic motion. It cannot be uniform. So here the velocity should be 0. Here it is maximum. Again it is retarding to 0 here. Then when the piston moves the next stroke from outer dead center to inner dead center, again during the first half the piston will accelerate. During the second half the piston will decelerate. So as the piston is accelerating, the flow in the suction pipe and the delivery pipe also have to accelerate and decelerate. So there will be additional pressure heads required for making these acceleration and deceleration. So the piston movement is not uniform. So we will discuss what is that acceleration head, how to find out that acceleration head. For that, actually we will consider that the piston is moving through, or the crank is rotating through an angle theta. We will consider that the crank is rotating through an angle theta here. When the crank rotates through angle theta, the piston is moving a linear distance of x, that is shown here. That x can be shown here also. This is x. Okay. So the crank is considered to be at a particular instant of theta. Then when the crank rotates through theta angle, the piston moves through a linear distance of x, that is shown here. Okay. Now what is actually x? X will be equal to, if this is r, the radius of the crank, this will be also r. So if this is r, if this is theta, this is r cos theta. So x will be equal to r minus r cos theta. So what is x? X is the movement of the piston through a linear distance when the crank is rotating through an angle theta. So x is equal to r minus r cos theta. Okay. So x is equal to r minus r cos theta. And what is dx by dt? That is the velocity of the piston. X is the distance through which the piston moves. X is the distance through which the piston moves when the crank rotates through an angle theta. And so velocity will be equal to dx by dt. It will be equal to dx by dt, and it will be equal to d by dt of r minus r cos theta. So it will be equal to 0 minus r into minus of sine theta, or sine theta can be written as sine omega t. Cos theta can be written as d by dt of r minus r cos omega t. Omega is the angular velocity for a time interval t. So theta is equal to omega t. Theta is equal to omega t. So it will be r minus r omega, r cos omega t. So on differentiating we will get it as minus sine omega t omega. So it will be equal to omega r sine theta, or omega r omega t, or omega r sine theta. So x is the distance through which the piston moves from inner dead center to outer dead center when the crank rotates through an angle theta. So that means the velocity of the piston is equal to dx by dt, and it is obtained as omega r sine theta. On differentiating this one, we will get it as omega r sine theta. Now we will apply the continuity equation. Continuity equation means discharge through pipe is equal to discharge into cylinder. Okay, so discharge through pipe means area of the pipe, area of cross section of the pipe into velocity in the pipe is equal to area and area of the cylinder into velocity of the cylinder, velocity of the piston. So discharge through pipe is equal to discharge into the cylinder. So discharge through the pipe is area of the pipe into velocity in the pipe. It can be suction pipe, it can be delivery pipe. So it will be equal to area of the cylinder or area of cross section of the piston, that will be equal to the area of cross section of the cylinder into velocity of the piston. So on applying, what will be the velocity of the pipe? Velocity of the pipe will be equal to A by A into V. V is here. So we can find out small v as A by A into omega r sine theta. So this is the velocity of fluid or water in either in suction pipe or in delivery pipe. If it is suction pipe, this area will be also that of the suction pipe, small a. Small a will be the area of suction pipe. Now what will be the acceleration? Acceleration of water in the suction pipe or delivery pipe will be equal to dV by dt. dV by dt. It will be equal to A by A omega r cos omega t into omega will be equal to A by A omega square r cos omega t. So this is the acceleration of water. Acceleration of water in suction or delivery pipe. It will be A by A omega square r cos omega t. Okay. So this is the distance x moved by the piston when the crank rotates through an angle theta. So on differentiating, we will get the velocity of the piston. So now then we will apply the continuity equation. This is the area of the pipe, discharge through pipe, area into velocity in the suction or delivery pipe. It will be equal to area of the piston into velocity of the piston. So we will find out the velocity of flow in the suction or delivery pipe as this much. So now the acceleration of the fluid in the suction or delivery pipe, that is equal to A by A omega square r cos omega t. Now we will find out, we are actually trying to find out the acceleration head, the pressure head required for acceleration of fluid in suction or delivery pipe. Acceleration head. So we have reached the acceleration. What is the amount of acceleration actually happening for the fluid in the suction or delivery pipe? Now we have to find out the pressure required for that. For that we will apply the Newton's second law of motion, that is force. Force is equal to mass into acceleration. Acceleration we have got. So what will be the force required? For that we will find out m. What is m? What is rho? Density of the fluid is equal to mass per volume. So mass is equal to rho into volume. So m is equal to rho into area. This is area into L. Means this is the area of cross section of the suction pipe or delivery pipe. This is the length of the pipe. It can be suction or delivery. So force required to accelerate water. Force required to accelerate water in a suction pipe or delivery pipe will be equal to mass into acceleration. mass we have find it as rho al. Then acceleration we have obtained as a by a omega square r cos omega t. So it will be equal to rho l a omega square r cos omega t. This is the force required to accelerate. And now the pressure, we have to convert it into pressure head. So first we will find out pressure intensity due to acceleration of water. Pressure intensity, the pressure developed, pressure intensity because of acceleration of water. It is equal to, pressure intensity is equal to force per unit area. So it will be equal to rho l a by a omega square r cos omega t. So this is the pressure intensity. Now we have to convert it into pressure head. So the pressure head will be equal to pressure head due to acceleration. How much pressure head is required for acceleration of water is equal to, pressure head is equal to weight of this pressure intensity P by rho g, that is the equation, no, P by rho g. So that is equal to rho l a by a omega square r cos omega t by rho g. So the acceleration pressure head, we can call it as HAS, is equal to L by G A by A omega square R cos omega t or cos theta. So A by A acceleration head is equal to L by G A by A omega square R cos theta. So I will say it once again. So we will consider a linear movement of x distance by the piston when the crank is rotating through an angle theta. So this is the distance moved by the piston x. So the velocity of the piston will be equal to dx by dt, and which will be obtained as omega r sin theta. So that is the velocity of the piston. So discharge through the pipe, continuity equation is applied, so that the discharge through pipe is equal to discharge into cylinder. The flow of water in the suction pipe will be equal to the flow of water into the cylinder. So if you consider this as suction pipe, this is the area of the suction pipe, this is the velocity of water in the suction pipe. It will be equal to area of the piston, cross-sectional area of the piston into velocity of the piston. So velocity of water in the suction pipe is equal to A by A into V. So A by A into omega r sin theta. Now we will find out the acceleration of water in the suction pipe. It is dV by dt. That is, we have to differentiate this one again. That will be obtained as A by A omega square r cos theta or cos omega t. So now acceleration is obtained, we have to find out the acceleration head. So we have to find out first the force, then the pressure, then the pressure head. So force is equal to m into A. So A, we know that is acceleration that we have found out here, A by A omega square r cos omega t. So what is m? M is equal to rho density into volume. Volume means volume of water in the suction pipe, area into length of the pipe. M is equal to rho AL. So force is equal to m into A, m into A, that is here. So rho L A omega square r cos omega t. Now that force is converted to pressure. The pressure intensity because of the acceleration is equal to F by A. So force by A, that means this A comes again. Then pressure head due to acceleration, pressure intensity by rho g, the weight of water. So rho g, that will be obtained as L by G, A by A, omega square R cos theta. So this is the acceleration head required to accelerate the water because of the acceleration of the piston during the first half of the strokes. Okay, this is the acceleration head. Now we will discuss what happens to the indicator diagram because of this acceleration head. Previously we have taken the indicator diagram that there is no other pressure heads. The simple indicator diagram here you can see we have considered only the vacuum created. No, we haven't considered the acceleration of the piston. So we have taken this HS as uniform along the stroke length on both suction and delivery. Now we are informed that there will be an acceleration head. There will be an additional pressure head required for the acceleration or deceleration of water inside the cylinder. So we have to consider that, and we have to redraw the indicator diagram considering the acceleration head. Okay. And for that, first of all, we have to find out what will be the acceleration head during the suction stroke at different positions of the piston. Okay, that is actually shown here. We can easily find out that. That means the formula is L by G, A by A, omega square R cos theta. The acceleration head HAS is equal to L by G, A by A, omega square R cos theta. So we can find out the value here when theta is equal to 0, when theta is equal to 90, and when theta is equal to 180. And you can see that when theta is equal to 0, cos theta is cos 0 is equal to 1. So it will be equal to L by G. When theta is equal to 0, it will be equal to L by G, A by A, omega square R, when theta is equal to 0. When theta is 90, we know that cos 90 was, what is cos 90? Cos 90 is 0. So this HAS will be equal to 0. When theta is equal to 180, what happens? Cos 180 is minus 1. So it will be HAS is equal to minus of L by G, A by A, omega square R. This happens in the suction side. Okay, this happens in the suction side. Similar will be the case with delivery side. Similar will be the same case with delivery side. So what will be the effect of acceleration head on the indicator diagram? We can look on to that. So this is the modified indicator diagram considering acceleration head also. So you can see the atmospheric pressure head, you can see the suction head shown in the dotted line, and at theta is equal to 0, you can see that there is an additional acceleration head which will be equal to L by G, A by A, omega square R. So an additional suction is required, additional vacuum is required, so that an additional vacuum of HAS is required other than this HS, so that the water is accelerated because of the acceleration of the piston from inner dead center to the middle of the center, so from 0 degrees from the inner dead center to half of the position of the piston, that means half of the stroke, the piston is accelerating, so an additional HAS is required, additional vacuum pressure head is required to meet this particular requirement. And at the end, at 180 degrees, it is negative, so that means that much vacuum less is enough at this point. So the modified indicator diagram will be like this. So this is the pressure position, an additional vacuum in the initial stage. It is not required in the middle position, and it will be negative in the outer dead center position. This is for the suction stroke. Similarly, for the delivery stroke, at zero position of the delivery stroke, that the outer dead center, it will be maximum. During the beginning, an additional pressure is required to accelerate water to compensate the acceleration of piston during the first half of the delivery stroke. Similarly, this is minus, so that much pressure can be reduced. So this is the indicator diagram. Now you can see that this is the modified indicator diagram. Okay. Now we will move on to another pressure head requirement, which is the frictional head. As we all know, there will be frictional losses in the suction pipe and delivery pipe. So that frictional pressure losses also should be included in the indicator diagram. What will be the pressure frictional head required? That is, we all know that equation, frictional pressure head equation. We are all familiar with that equation of frictional head. That is, HS is equal to head loss due to friction. Head loss due to friction. Due to friction. We are all familiar with that equation. HS or HFS, we can say, is equal to 4FL by 2GD, 4FL V square by 2GD, where V is the velocity in, for if we are finding out the friction head loss in the suction pipe, this will be LS, the length of the suction pipe. This will be the diameter of the suction pipe. This will be the coefficient of friction in the suction pipe. This will be the velocity of flow in the suction pipe. So that velocity we are all familiar. We have find out with that velocity. What is that velocity? A by A omega r sine theta the whole square. So that means head loss due to friction is proportional to the square of the angle theta turned by the crank. Therefore, the variation of head loss due to friction, HF, with crank angle is parabolic. Because of this particular proportionality of this HFS is directly proportional to the square of theta, then it can be seen that it is parabolic. Okay. So now if we apply for the positions theta is equal to 0, theta is equal to 90, and theta is equal to 180. You can see that at theta is equal to 0, this will be 0. At theta is equal to 180, again this will be 0. But at theta is equal to 90, it will be maximum. So the indicator diagram will be like this. During the suction stroke, we are actually showing only the frictional head. We are not showing the acceleration head here. There is acceleration head also. We will combine all these in the next figure. So here this is the simple indicator diagram. You can see the simple indicator diagram here. This is the atmospheric pressure head, and this is the suction head, and this is the delivery head. So if you consider the frictional head also, it will be a parabolic one, and it will be 0 at 0 angle and 180 degree angle. It will be maximum at the 90 degree angle. So it will be like this. The pressure variation in the cylinder from 0 to 90 and from 90 to 180. Similar is the case with delivery pipe. So if you combine all these, the acceleration head and the frictional head, the indicator diagram will be like this. So if you can see here, this is the simple indicator diagram here. This is the atmospheric pressure head. If we consider the acceleration head, initially there will be an additional vacuum requirement, and it will be like this in different positions. And this is the, for the delivery stroke, this will be the acceleration head. So this is the acceleration. pressure variation shown. And now if we consider the frictional variation also, frictional pressure head also, it will be like this. So this will be the actual indicator diagram area. This will be the actual indicator diagram area, and the area of the indicator diagram actually indicates the work done. It is proportional to the work done by the pump. The actual area of the indicator diagram is directly proportional to the work done by the pump. That means you can see here the actual area. If you look on here, the actual area of the indicator diagram, it will be equal to this much area into the parabolic area, two parabolic areas. This much area plus the two parabolic areas, it will give the total area of this indicator diagram, and that is shown here. I am not going to write this, it is shown here. The total area will be equal to length into HS plus HD plus, so the two parabolic, you can see here the two parabolic areas will be 2 by 3 into L into HFS and 2 by 3 into L into HFD. The two parabolic areas, these two parabolic areas, the area of the parabola, length into 2 by 3 L into HFS plus 2 by 3 L into HFD. This is the two parabolic area, and the area of this rectangle will be L into HS plus HD. So this is the total area of the indicator diagram. So this is the indicator diagram. You can see the indicator diagram here, and you can see the total area. Total area will be equal to here L into HS plus HD for the rectangular part, plus 2 by 3 L into HFS plus 2 by 3 L into HFD, the two parabolic area. So this total area is proportional to the work done by the pump. Total area is proportional to the work done by the pump. Okay. Now we can actually do a problem. I am not going to do the problem here. I will discuss the problem and you may go through the problem. It is a solved out problem which on the notes which I have already given to you. So this is the problem. You can see a single acting reciprocating pump has a stroke length of 18 centimeter. Suction pipe is 8 millimeter long and the ratio of suction pipe diameter to the piston diameter is 3 by 4. The water level in the sump is 3 meters below the axis of the pump cylinder, and the pipe connecting the sump and the pump cylinder is 8 centimeters in diameter. If the crank is running at 60 rpm, determine the pressure head on the piston in the beginning, in the middle, in the end, taking coefficient of friction as 0.01. So this is a solved out problem. You can go through the notes. And another important component of a reciprocating pump is an air vessel that we will discuss in the next session. I will give it as another session. Okay, thank you.